So is it visible to you? All of you? My screen is very visible. So today we are going to discuss about the controllers. Okay. So what is a controller? Already we have discussed about the controllers, so which act on error signal and improve the transient and steady state performance of a system. Okay, so already we have discussed completely about the proportional, integral, and derivative actions in our second unit. Okay, so once again I will go through these controllers. So how they are useful in improving the performance of a system. Okay, so just we'll recall the system. So this is a closed loop system normally. So which is control, which is having the input signal, output signal, okay, and then the error signal here, which we call it as a, this function is called as a error signal. This is an input signal, okay, and now this is an output signal. This is a feedback signal, and it is a unity feedback. And now we are considering this as a noise signal. Okay, we can also measure the noise in the system. Okay, so whenever the noise is present in the system, we can also include in a feedback system. And if there is any disturbance in the signal, this can be included here. So this is a complete closed loop system. Now this is also called as a feedback system. Okay, so the feedback system has the advantages of it improving the stability. Okay, so this can improve the stability and meeting the performance of a performance specifications. Okay, so this can be taken as a time domain specifications or frequency domain specifications. So, and decreasing the sensitivity to parameter variations. If any parameter is varying and the parameter variations at the output side will be decreased by automatically sensing the feedback signal, and it is comparing with the reference signal, and it is providing the error signal. Okay, now this is your controller. This is a controller, and your G of S is your plant. Okay, so in all previous cases, we assume that there is no disturbance in the system. Okay, and directly we have taken this one. Okay, so and also it has the improving the disturbance rejection. So if any disturbance is present, automatically there is a change in the output side. Okay, the signal will be varied, and the change in output can be sensed, and it is compared with your reference input. Okay, so this is called as your reference input. Always it is continuously measures the output signal, and if it will produce the error signal, and this will provide an output signal which is controlled by your controller. So your plant is producing the desired output. So this is desired output automatically developed in a feedback system. So this is advantage of your feedback systems. Okay, and attenuating the measurement of noise. So if there is any noise in the system, it can also be included here, so that your reference signal is comparing this noise also, and it is providing the desired output. So these are the advantages of a feedback or closed loop systems. Okay, so this we have discussed. And now the performance specifications of our first order and second order systems also we have discussed. So normally the first order system is defined as, it is normally 1 by 1 plus t into s, or you can also consider this as a k by 1 plus t into s. So where t is the time constant of a first order system, which we have discussed already. Okay, And then the second order system, which is defined like this. So omega n square by s square plus 2 zeta omega n into s plus omega n square. And we identified some features and captured the natural nature of the responses for the second order system, so which are called as the time domain specifications. Here we have discussed about the rise time. So the rise time formula is given by pi minus theta by omega d. Okay, and delay time, and also the percentage overshoot, settling time. These are the performance specifications in a time domain which we have discussed already. Now, so here we'll see the dominant pole. What is the dominant pole of the system? So here this is a complex pole. Okay, so in a complex system here, there are different poles and zeros which are located in the left half of the S plane. So for a higher order systems, so there are more number of poles and zeros which are distributed in the S plane like this. Okay, so here the poles which are very nearer to the imaginary axis are called as a dominant poles. Okay, so we'll see what is the contribution of these poles and zeros to the system. Okay, so the poles closest to the imaginary axis have the most dominant contribution and are called as the dominant poles. So the poles which are closer to the imaginary axis, we call it as a dominant pole. So we'll see what is the effect of these poles on the system. Okay, so here if you assume that there are complex poles which are very nearer to the imaginary axis, now we'll analyze the systems by adding an extra pole and zero to the dominant system along with the dominant poles. Okay, so these are the topics which we have left in step third and fourth unit. So what are the effects of addition of poles and zeros to the system? So easily you can understand the concept of addition and addition of poles and zeros into the system. Now, so effects of addition of a poles and the zeros. Okay, so consider a second order system. Okay, so we are considering the second order system. So the standard form of a second order system is given by C of s is equal to omega n square divided by s square plus 2 zeta omega n into s plus omega n square. Then for simplicity, we are assuming that zeta is equal to 0.5 and omega is equal to 1. Zeta is equal to 0.5 and omega n is equal to 1, which is a natural frequency. So this will give you a system characteristic equation like this: s square plus s in s plus 1, because omega n is equal to 1, so omega n square is equal to 1. So this will be 1 divided by s square. Okay, your system is s square plus zeta is 0.5, so 2 into 0.5 is 1, omega n is 1, so you get it as a s plus 1. So this is your system. Okay, now we are starting our system response by adding s is equal to minus a. So we are adding a 0. Okay, so we are adding a 0 at s is equal to minus a. So we can see that what is the effect of this 0 on the system. Okay, so now to maintain a DC gain constant value of 1, now we are adding a pole as a 1 by s plus a plus 1. So this is a 0 now here. Okay, so we are adding a 0, 1 by s by a plus 1 divided by this s square plus s plus 1. This is your system. So your new transfer function now C1 of s. Okay, so C1 of s will be equal to, this is normally T of s. Okay, so it is not the output actually. So this is a system response. Okay, so this output, so C of s by R of s. Okay, so this is normally we can call it as a C of s by R of s, as we know that. Okay, so this is an output function. You can also call it as a y. So here now instead of that, now C of 1 of s. Now the new transfer function which is given like this with the addition of zeros into the system. Okay, so addition of the system will be now making it as a 1 by s square plus s plus 1 here. Now the next term will be s by a. So s by a, 1 by a, I can take it as a 1 by a into s by s square plus s plus 1. So I'm separating these two forms. So you will get 1 by s square plus s plus 1 plus 1 by a into s by s square plus s plus 1. So let us take the inverse Laplace transform of these functions. So this will give you inverse Laplace transform of c of s will be equal to c of t, and inverse Laplace transform of c1 of s is equal to c1 of t. So here c1 of t will be equal to c of t plus c of t plus, here this is a constant term, 1 by a into c dash of t, because this is a c, then if you multiply this with s, this is going to be c dash or c dot of t. So this is your response. So this response consisting of your original response c of t plus the response with this, which is added with a 0 at a. So you can understand that by adding a 0, you can the response of a system will be varying. Now here, the net output of a response of a system for a unit step input is nothing but your c of s. Y of s is equal to c1 of s into 1 by s. Okay, so here c1 of s is your output. Originally c1 of s is your original system with a as addition of a 0. So your output response y of c is equal to c1 of s into, we are interested in finding the step response of a system. So normally the step response means you have to apply the input of a. So this is a 1 and this is u of s. The signal will be u of s, which is reference to t. And therefore, by adding this signal, your y of s, output signal y of s will be equal to c of s by s plus s by a into c of s by s. So here, this will be equal to, this is a c dash. Normally, this is a c dash of s. Okay, 1 by s. So s into c of s will be nothing but your y1 of s. Okay, so this y1 of s, c of s by s is a y1 of s, we are calling it. Then s by a into c of s by s is again 1 y1 of s. So again, we are taking the inverse Laplace transform to the system. So y of t. By taking inverse Laplace transform, you can convert s domain into time domain. So y of t is equal to y1 of t plus 1 by a into y1 of y1 dash, because here this is a s term is there, so this is a d by dt of y1 of s, and therefore you get a this value of y1 dash of t, with y2 of t is equal to y1 dash of t. We can have y of t will be equal to y1 of t plus 1 by a into y2 of t. So y2 of t is nothing but the same system, but it is a differentiation of your original function. So we will see the responses separately. Okay, so what is the response of y1 of t? What is the response y2 of t? And what is the response, the net response y of t with the variation of your 0. So you are adding a 0 at the point. Okay, so for different values of a, we see that how this y2 of t is varying, y1 of t is varying, and the resultant of these two is nothing but your system response, complete response y of t. We'll see here. Okay, so in this case here, the red line, the red signal indicating your net response y, black signal is representing y1, and the blue signal is representing y2. Okay, so if you add a 0 at s is equal to minus 0.5, so this is the response here. Now if you add a 0 at minus 1, so the response here. So you can observe that by adding a 0, your response blue line is varying now. Okay, so here if you add up 0 at -8, that means it is far away. So I'm adding a 0 very nearer to the imaginary axis here. Okay, and 0 at -1 and 0 at -8. So if you add up 0 at -8, that means it is far away from your imaginary axis, like this here. Okay, so this is your real imaginary axis, and this is a real axis. So you are adding at 0 at -0.5 and 0 at -1 and 0 which is far away from this system which is at -8. Okay, so by observing this is a 0 at -1 and this is a 0 at -0.5. So these are the three responses. By observing these three responses, okay, so there is an increased overshoot here. Initially, this is our required system. The black line must be the required response. Okay, so this will be required response. Without zero, you will get a response like this. The black line is our required desired response for the system. So if you add up a 0, so the net response of the 0 is like this blue. So the net response, which is nothing but here red signal. So by observing this, so response overshoot is increased. Okay, so increased overshoot. Overshoot of the system is increased. Now there is no significant change in the settling time. Just if you observe this, is there any change in the settling time? So here for the black line, this is your settling time TS. For after adding a 0 also, you are getting a TS only here the same time, and the response is faster again. Okay, in both the cases here, in the second case also, if s is equal to -1 also, the response overshoot is increased. So whenever it is far away, the overshoot as compared to the first case, the overshoot is reduced. Okay, so the peak overshoot is reduced if the 0 is away from your first place. So the peak overshoot is reduced, and settling time is also slightly improved. As compared to the first case, the settling time is slightly, very slightly, it is improved. So you can say that the response is faster. And now, in the third case, if it is located at -8, if it is located at -8 means it is far away. So the output response is similar to your original response. So there is no effect of 0 on the system. So because the red line and black line, both the signals Y and Y1, both are same magnitudes, rather than same response. So there is no effect of your response Y2, that is pole at -8. Okay, so as the pole alpha tends to infinity, the contribution of the 0 to the system response decreases, and we get back to the original behavior. So this black line is our original behavior. So if the pole is located very nearer to the imaginary axis, okay, so 0 is located very nearer to the imaginary axis, the peak overshoot is increases, the settling time is no change, and when you locate the pole at -1, this is the response here. Again, the response is having a peak overshoot is slightly decreased. So here the peak overshoot is up to 1.6, but here the peak overshoot is up to 1.3 only. This is 1.3 and here 1.6. The peak overshoot is reduced and the settling time is slightly reduced. So the response is faster. And if you locate at -8, again, the response is faster and the peak overshoot is very less. The peak overshoot you can observe here, which is below 1.2. Here this is 1.3, but here the peak overshoot gets reduced. So this is the advantage of uh, adding the 0 away from the imaginary axis. So this is the effect of addition of a zero in the left half of the S plane. Now, let us see what is the effects of adding a zero in the right half of the S plane. So in the right half of the S plane means S will be equal to A, which is having a positive sign. Okay, that means here S is equal to a positive real part. That means 1 minus S by A. So the negative sign. You'll get here C1 of S will be equal to, the system is same original system here, 1 by S square plus S plus 1 minus 1 by A into 1 by S square plus S plus 1. Okay, so this is your response, and the response will be having a negative sign for the second function. So this is a negative. So C1 of t will be equal to C of t. This is the response with C of t minus 1 by a into C dash of t. Okay, so this function, this should have S by a. So this should have S by a, or you can call it as a connect 1 into S by something. Okay, so this is a constant value. Okay, 1 by a into S by, this is not there, S by S square plus S plus 1. And therefore, the system response will be equal to Y of S is equal to C of S into 1 by S. This is your input signal. So C of S is nothing but your C1 of S. So C1 of S is C1 of S divided by S minus S by A into C1 of S by A. So again, your output signal Y of t will be equal to Y1 of t minus 1 by A into Y dash of t. Y dash of t, you can call it as a Y2. So with the addition of 0 to the right half of the S plane, your response will be now sluggish. That means here it will have a undershoot, and it takes far time so that you'll get a sluggish response in the system. So increasing the rise time and delay time. Okay. So there is an undershoot in the transient response for small values of A, and then undershoot leads to sluggish response, and with an increase in the rise time and delay time. Okay, so here that's why the poles and zeros in the right half of the S plane are called as a non-minimum phase poles or zeros. So the systems which consisting of poles and zeros in the right half of the S plane are called as a non-minimum phase systems. Non-minimum phase systems. So now let us add a pole. Now let us add a pole in the left half of the S plane. Instead of adding a zero here, we'll see if you add a pole in the left half of the S plane. So that is 1 by S by A plus 1 into your original system 1 by S square plus S plus 1. Okay, so if it is added at which is nearer to the imaginary axis, so your response will have this response will be now no oscillations in the system. There are no oscillations in the system, and if it is added away from that, again this will be improves. It is improves the transient response, and in the last case, if it is located at -5, the response is similar to your original response. Okay, so if you add a pole very nearer to the imaginary axis, the response is very faster. Okay, so if you add up this response is like this. Now second case it is -2.5. Okay, so as A is nothing but the pole tends to infinity, the contribution of the pole to the system response decreases, and we get back to the original behavior. That means if you add up the poles which are away from your imaginary axis, the effect of pole in the system is less. There is no effect of poles and zeros on the system. In previous case also, as zero is also located very nearer to the system, the system response increases, and the overshoot increases. Here, if you add that the overshoot is not there, the pole is added, there is no overshoot here, the overshoot is reduced, and your response is improved. Okay, so in the design process, as a thumb rule, we roughly take that the pole which is 5 times the real part of a dominant pole. That's the pole, whenever you're taking a pole, that must be greater than 5 times of the real part of the dominant pole. So we have seen that the dominant poles are nothing but the poles which are located as a complex conjugate, which are very nearer to the imaginary axis, which are nearer to imaginary axis. We call these poles as a dominant poles. Now, if you want to add up a pole, this should be taken with the 5 times of this dominant pole, so that the effect on the system is not there. Okay, so there is no change in the system response. If you want to improve the response, you have to add the pole with zeros. So now the dominant poles. The dominant poles are the closed loop poles that have the dominant contribution and the tangent response of the system. It is often that the case that these dominant poles occur in the form of complex conjugate poles. So these are nothing but the complex conjugate poles. These are the complex conjugate poles. So for higher order systems, there exists a pair of dominant complex conjugate poles. Okay, so higher order systems are generally adjusted such that there exists a pair of dominant complex conjugate poles, and it is desirable to have the real parts of the other poles and zeros at least 5 times farther away than the real parts of these dominant poles. So if you take a zeros or poles, so they should have, so if this is a -1, okay, so the real part of this is -1, then at least 5 times. So whenever you are taking poles and zeros, this must be of having a -5 plus or minus j something. Like that you have to consider. Now, let us see the effect of adding poles to the open loop transfer function. Okay, so the addition of poles to an open loop transfer function has the effect of pulling the root locus to the right. Some of the closed loop poles are nearer to the imaginary axis, which implies the relative stability is reduced. We have seen that whenever we move away from the imaginary axis, the stability of a system increases. So we begin with a single loop system and progressively we illustrate all these problems here. So this is a root locus for a system g of s is equal to 1 by s plus 2. So 1 by s plus 2 means a pole is located here at s is equal to -2. So we know that how to draw the root locus techniques. Okay, so first of all, we need to find the root locus path. Okay, so root locus path means how the root locus is varying with the value of k. So k is varied from 0 to infinity. When we vary k with 0 to infinity, so how the root locus is varying towards the imaginary with the negative real axis, or it is moving towards the right half of the spline, or moving along only in the left half of the spline. Like that we have to estimate, so that you can say the stability of a system. Okay, so if you take any point in between -2 and infinity, -2 to minus infinity, okay, so this is a part of root locus. This is a completely a root locus part with the k is varied from 0 to infinity. So you see that the root locus is moving only in the negative of the s. So the system is stable. So it is completely stable. The system, whatever may be the value of k, the system is stable here. So in the second case, if we add up one pole to the system, one pole is added at -4. So this is a -2, okay, and this is a -4. Let us assume. So if you take up any point between 0 to -1, this is a part of a root locus. -2 to -4 is only the part of root locus, because if you take any point in between that, to the right of that point, the number of poles and zeros are odd. Okay, so this is a part of root locus. So -2 to -4 is a part of root locus, and from 0 to -2 it is not part of root locus. So here these thick lines will indicate the root locus part. And also if you take up that -4 to infinity, this is also not part of root locus. And therefore, we need to see that how these roots are moving in a direction, in which direction. So here we can find that the centroid will be equal to -2 and -4 divided by 2. So this will be equal to -3. So this is a -3, the centroid, and then the angle of asymptotes is 180 degrees by 2. So it is always 90 degrees. The angle of asymptotes are 90 degrees each, and the meeting point of the angle of asymptotes is called as a centroid. And also you find the breakaway point where this is breaking up. Okay, because this pole will be moving in this direction and this pole will be moving in this direction. At this point, this will breaks away. So we'll know that the breaking point is -3. You can calculate also. So we'll get the breaking point here. With the 90 degrees, these two roots are moving towards the infinity. This is also moving towards the infinity. The number of root locus branches which terminate at infinity is equal to n minus m or p minus z, which is number of poles minus zeros. So here there are two poles. So these two poles will terminate at the infinity only in the left half of the S-plane. So the system is also stable here. The system is stable in the second case also. If you add up a pole to the system, again the system is stable. But now one more pole is added to the system here. Okay, in the last case, one more pole is added. So this is a -2, -4. This is the one pole. Okay, pole. This is a -4, and this is a -8. This pole is at -8. So -4 to -8, it is not a part of root locus, because if you take any point here, here, the number of poles and zeros are 2. Addition of poles and zeros are 2. So this -4 to -8 is not a part of root locus. But -2 to -4 is a part of root locus. And from -8 to infinity, minus infinity is a part of root locus. Okay. So there are 3 root locus branches which terminate to infinity, the n minus m, because there are zeros are 0. So 3 root locus branches terminate to infinity, and this will terminate to infinity with the angle of asymptotes of 180 degrees by 3. 180 degrees divided by 3. So this is nothing but plus or minus 60 degrees. Plus or minus 60 degrees, and one more is plus or minus 180 degrees. Okay, so here with the centroid, they will terminate to the infinity, and in this process, they will cross the imaginary point. They will cross the imaginary axis. So in this case, the root locus is moving towards the right half of the S-plane. So in the second case, when k is varied from 0 to infinity, 0 to infinity, the root locus is located only in the left half of the S-plane. So the system is stable. But in the third case, if there is a limited value for k is limited up to this point only, the system is stable. If the k is greater than this point, the system may be unstable. So this is the effect of addition of poles to the system. So how this root locus is moved. Okay, so let us take that 0 now. So effect of addition of a 0. So in previous case, if you add up a pole, the root locus is turning towards the right half of the S-plane. So here it is completely in the left. Now in the second case, it will be shifted slightly to the right side. And in the third case, it is moving on to the right half of the S-plane. But now if the addition of 0, your original system, which is located in the right half of the S-plane, will be shifted to the left half of the S-plane. So this is the advantage of adding a 0 into the system. Okay, so here the first case, there is no 0 in the system. Okay, one pole is located at origin and -2 and -5. So this is a part of a root locus, and this is a part of a root locus. This is a part of root locus, and this is moving towards the infinity. and here this pole is breaking away, okay, at this point, and it is moving towards the infinity along the right half of the S plane. Now, if you add up a 0, this will be slightly moved. So it is not moving towards the infinity. It is moving only along the imaginary axis. So the stability is slightly improved here. Okay, now if you add up pole, if you add up 0 at -3, so here we are adding a 0 at -7. So -7 means it is slightly reduced. If you add up at -3, S is equal to -3, so your root locus is shifted to the left half of the S plane only. Okay, so here you see that the root locus is shifted to the left side and it is moving only in the left half of the S plane like this. Now, if we add up the 0 at -1, 0 at -1 here, this is a 0. So this pole is terminating at this 0, and here this pole and the next pole here, there is a breakaway point, and the root locus is again shifted. The root locus is shifted to the left side. So the stability of the system increased. So whenever you add up a 0, when you add up a 0 into the system stability improves. And if you add up a pole into the system stability the system stability reduces. Okay, so as part of the root locus is concerned, if you add up a pole, the root locus is moving towards the right half of the S plane. If you add up a 0, the root locus is moving towards the left half of the S plane. Now let us take this with the proportional controller. So by the addition now here, so the controllers act on an error signal between the reference input and the measured output. Okay, so we have seen the Nyquist plot, root locus, and Bode plots. So we'll see what are the additions of K. So if you add up again K, so the system stability, the margin of the system stability can be increased onto the system. Okay, so with the freedom of varying, only with the gain K, we are restricted to move on the root locus. So works when the poles and the root locus meet the specifications. So if not, more sophisticated controllers are necessary here. So this is a root locus part of a system for a given transfer function. Now see that the effect of this on the Bode plot also. With the same, the system is K. This is a proportional controller. If you add up, only you are controlling the K value. There is no effect on the poles and zeros with this proportional controller. Okay, so now onwards I will consider only the proportional constant K, 1 by S and S, proportional derivative and integral controllers. We'll see how this is affecting the system. Okay, so in the root locus, we have the option of only varying the gain K, but there is no control over the poles and zeros in the system. Okay, so the gain K is varied from 0 to infinity, so it will not affect the position of your root locus. So, but you can get restricted to the stability of the system for the given value of K. So similarly in Bode plot also, your gain can be controlled so that your Bode plot can be reduced, moved in the up or down sides, so that you can increase. There may be sufficient gain margin and phase margin can be allowed into the system. Okay, so here whenever you vary the gain, so this may be gain for different gains. Here this is a gain K is equal to 1. So you have the option of adding the gain so that your Bode plot can be shifted in the up and down. Okay, so that you'll get a specified gain margins and phase margins. And again, so to get a specified phase and gain margins, we need some controllers in the system. So those controllers are called as a proportional, integral, and derivative controllers. Okay, and also we can call it as a compensation methods. Okay, so There are two types here. You can also use the proportional control, PID controllers, or also the compensation methods. So to get this specifies performance specifications of a system, we require the controllers or compensation methods. This is our conclusion from the addition of poles and zeros to the system. Okay, so we'll see one by one. So what is the controller, how it is affecting the system performance. Then we'll see the compensators, what are the different compensators, how they can be used to improve the performance of a system. So now let us take the proportional controller. So here G of S is equal to K by Ts plus 1. This is the complete transfer function of the system with a proportional controller K. Okay, so this is your 1 by Ts plus 1 is the system or plant transfer function. K is the proportional controller, P controller. So your error signal will be given as 1 by 1 plus G of S into R of S. So R of S is your input, and you substitute for G of S in this equation 1 by 1 plus K by Ts plus 1. This will into 1 by S. So this will give you the transfer function of Ts plus 1 plus K, okay, and in the denominator, and Ts plus 1 in the numerator. So this Ts plus 1 term can be the numerator term, then 1 by S is your input signal. Then as per the definition of the steady state error, the steady state error is equal to limit t tends to infinity into E of t, or limit s tends to 0 s into E of s. So this limit s tends to 0, if you substitute for s tends to 0 here, you'll get a steady state error of 1 by 1 plus k. So the proportional controller has improved the time constant, because the time constant has been varied with t2 t by 1 plus k. So here k is a positive value always, and therefore the time constant of the system is improved. So in previous case, without the controller, the time constant was t. With the proportional controller, the time constant is changed to t by 1 plus k. So the time constant of the system is reduced. However, the steady state error is present in the system. So there is no change in the steady state error with the proportional controller action in the system. So the steady state error can be reduced by choosing a large value of k. But high gain has the tendency to destabilize the higher order plans. So we have seen by using the root locus or Raut-Hurwitz criteria that if you go on increasing the system gain k, the system may become unstable. So this is a disadvantage of a higher value of k, increasing the k to higher values. Now, let us take the integral controller. So the integral controller is nothing but it is having a gain value of k by s. Normally we have taken this as a ki by s. Okay, integral gain ki divided by s in the second unit what we have discussed earlier. Okay, so here the output of the controller will be now output of the controller will be equal to k by s into E of s, because this controller is operating on the error signal. So the output of this controller will be equal to k by s into E of s, which can be taken as yc of t will be equal to sub k into integration of minus infinity to t into E of t into dt. And therefore now, by using this controller design, we can take the error signal as E of s is equal to 1 by 1 plus g of s into h of s into r of s. So this will be equal to s into ts plus 1. Just you substitute here. So g of s, complete g of s is equal to k by s into ts plus 1. So you can substitute here. We are finally going to get this transfer function as s into ts plus 1 divided by s into ts plus 1 here. S into ts plus 1 plus k, okay, into 1 by s. This is our input. So the steady state error is given as limit t tends to infinity into E of t, or limit s tends to 0 s into E of s. So in the numerator term, this will be now here S, and S will be cancelled out. But here you'll get it as a S square term. S and S will be cancelled out, but one more S is there. If you put S is equal to 0, the net term is going to be 0. That means the steady state error has become 0. The steady state error is 0. So with the integrator as the controller, the steady state error is now 0. The steady state error is 0. So note that the order of the system has increased from 1 to 2. Initially the order is 1, order of the system is 1, but with the addition of integral controller, the order has increased from 1 to 2 and the steady state error become 0. Okay, so as we seen from IRR systems, addition of an extra pole may lead to instability. Addition of a pole may, so we have seen that addition of a pole makes the system unstable. Initially, when the root locus on the complete left half of the S plane, so it is shifting towards the right side. So the addition of a pole into the system leads to the instability. But here, where error may be 0, but the system may become instability. So the compromise should be there between the error, steady state error, and the time domain specifications, and also with the stability of a system. So just as an exercise, you do this problem. Okay, just find out what is the stability of a system by addition of k by s to the system. Here 1 by s into js plus b. This is a second order system. This is a second order system. If you add up integrated to the system, what about the stability? Now, the response in the presence of external disturbances. So here I'm considering second order system. The second order system transfer function is given as g of s is equal to 1 by s into js plus b. This is a planned transfer function. So the modals or a rotational element, because this is a j moment of inertia, okay, and viscous coefficient function b, which we are considering for the system. And now there is a disturbance in the system. So how the response varies with the disturbance. So the controller has access to the input torque. Okay, this is the input torque T of S. Okay, so this is a torque T of S, and external disturbance D of S acts as the input. So now this is the system input now. So the R of S input will be taken as a 0. Now you are taking the transfer function y of s by d of s. So y of s by d of s is equal to 1 by j s square plus bs plus k. So because this is a k, okay. So this is your transfer function. Now the error signal e of s by d of s is equal to minus y of s by d of s, which is equal to minus of 1 by j s square plus bs plus k. And the steady state error ESS is equal to limit s tends to 0 s into E of s, which is given as the minus t by k. So with the effect of the disturbance in the system, the steady state error is minus t by k. So but the steady state error can be reduced by increasing the value of k in k. However, the system becomes more oscillatory. So for higher order plants can lead to the instability of the system. With the increase of k, the systems will become unstable. Now, let us consider that the proportional plus integral controller. So let us do proportional plus integral controller on the system. The new transfer function is given as y of s by d of s, which is equal to s by js cube. This is a second order system. Now you are adding a proportional term. So this is a proportional term plus integral term here. So k by t by k divided by ti by s. So your system will become, here also we are assuming that the r of s should be 0. Okay, so in previous case we assumed that the steady state error is minus t by k, and the system is unstable. So by adding the proportional plus integral controller, we see that if the steady state error is going to zero or not, and the stability of the system increases or not. Okay, so by applying this, the characteristic equation of the system is nothing but JSSQ plus BS square plus KS plus KI divided by KI 0, and have a negative real part here. The characteristic equation has a negative real parts, and if we find out the steady state error for this, the steady state error is going to be 0. So we can conclude that the addition of the proportional plus integral controller action can be eliminates the steady state error, and the system becomes more stable. Okay, so in this case, the proportional controller ensures about the stability, and your integral controller eliminates the steady state error. So this is the advantage of using a proportional plus integral controllers in the system. So if you use only an integral controller, it leads to instability of the system. It may eliminate the steady state error, but it leads to the system to be unstable. And that's why we have to use the proportional controller in conjunction with the integral controller, so that the proportional controller ensures about the stability, and the integral controller eliminates the steady state error. Now let us consider again another system. G of s is equal to 1 by j s square. We use the proportional controller here. With the proportional controller, the closed loop transfer function is given as k by j s square plus k. So the poles of the characteristic equation are on the imaginary axis. That means here j square plus k. So s square, the poles will be nothing but s square will be equal to minus k by j, minus k by j. So this can be taken as a s is equal to plus or minus root of minus k by j. So these roots are located on the imaginary axis. So the response is oscillations. The response is having the oscillations in the system. So these oscillations can be damped. These oscillations can be damped if we incorporate a derivative term in the controller. So we'll see that. So if we add up a proportional plus derivative controller into the system, so the proportional and the derivative controller can be taken as k. K is the proportional controller plus k td of s. This is called as a derivative controller. If we incorporate this into our system, so this will change the steady state error. So k into e of s plus k into td into s into e of s, and therefore yc of t will be equal to k into e of t plus so do you have any problem now? Are you listening? All of you are listening? So with the addition of proportional and integral controllers, we need to eliminate these problems of the steady state error and stability. So the derivative term acts on the rate of change of error signal, and the output is proportional to the rate of change of error signal. And therefore the derivative term anticipates the large overshoot, and when the rate of change of error is high, and takes the corrective action. So the effect can be noticed in the improved damping in the system. And therefore here the proportional plus derivative controller action for the system is like this. Now let us take the proportional plus derivative and integral controllers. So initially this is a system 1 by s square minus b. Okay, so 1 by s square minus b is your original system. Now with b greater than 0, the system is unstable with the poles at s is equal to plus or minus j root b, because these poles are located on the right of left of the S plane, so the system is unstable. So now we use the proportional controller. So with the proportional controller, your response y of c, the closed loop transfer function y of s will be equal to kp divided by s square minus b plus kp. So the system cannot be stabilized by using just proportional controller, because you are adding a pole to the system, the s square term. S is equal to now s is equal to minus b plus or minus root b. So just you are adding a some gain constant to the system. So the poles which are located in the left side and right side of the system. So by making a just proportional controller, this cannot make the system stable, because the position of pole is changing in the right half of the S plane, but it is not moving towards the left half of the S plane. So your only proportional controller doesn't make the system to be stable, and therefore we use the proportional and derivative controller here. So with the proportional and derivative controller, for kd greater than 0 and kp greater than b, the system is stable, and arbitrary pole placement is possible. So arbitrary pole placement means the poles which can be located in the left half of the S plane from the right. So the closed loop systems can be now placed in the S plane to meet any given specifications in the system. So this is your transfer function, which is nothing but s square plus kd into s plus kp minus s. You can use your Router-Ridge criteria or pole placement methods, whatever it may be. Just you see that the system will become stable for kd. Kd is nothing but the uh, derivative constant of a derivative controller, and kp is the gain of a proportional controller. So this proportional controller gain must be chosen such that kp must be greater than b and kd must be greater than 0. So your arbitrary pole placement is possible in the left half of the S plane. So the system is stable. The system is stable. Now let us take this with the PID controller. So for the PID controller, now we see the steady state error. So the steady state error and DC gain of the system. So DC gain of the system can be found as a limit s tends to 0, s into y of s. This is a steady state error. Okay. So this is steady state error is equal to Kp divided by Kp minus b, which is not equal to 1. Okay, this DC gain is not equal to 1, and the error is also not equal to 0. So whenever the error is not 0 and the DC gain is not equal to 1, now you can add up an integral controller to the system. So we'll study that how you are getting the DC gain. Okay, so if you add up a DC gain into the system, so your new transfer function will be like this: Kp Kd plus Ki by s into 1 by s square minus b. So we are studying here, we are studying the effects of PID controllers into the system, how this will be affecting your original system performance. Okay, so original system is unstable because s square will be s is equal to your original system, s is equal to plus or minus root b. So one pole is located on the right half of the S plane and one pole is located at the left. Okay, so this is the right half of the S plane and this is located on the left half of the S plane. So if you see this, the system is unstable. This original system is unstable, and we have to design our controllers in such a way that the system will become stable. Okay, so we have seen all the cases with the addition of a proportional controller. If you add up only the proportional controller K, the location of these poles are same, so the system is unstable. So there is no effect of adding only a proportional controller. Now let us take the proportional and derivative controller. in this derivative controller, so DC gain is not equal to 1 and the system will have a steady state error. So that's why we are going for the addition of PID controllers. Okay, so here there is a PD controller is there. Now we are adding up an integral controller into the system. Therefore, your DC gain is becoming 1 and now the steady state error will become 0 here. Okay, so because the S term is there in the numerator, so this S term will become, the steady state error will be a constant value. Okay, so it will reject the constant disturbances from the input system. And therefore, now we can conclude that the PID controller will stabilize an unstable second order system through the multiple degrees of freedom offered by the PID controllers. We can place the poles arbitrarily in any plane in this plane. So the system has a perfect tracking of our step signals because of integral control, and also the system rejects constant disturbance inputs. So these are the advantages of PID controllers into the system. So shall I stop here? Shall I stop here? Can we see the remaining class tomorrow? So with the effect of compensators. Okay, so here up to now we have discussed about, so what are the conclusions from today's class? What we have discussed today? So we have discussed about the addition of poles and zeros to the system. So what are the effects of addition of a pole and zeros to the system? So how they are controlling the root locus and Bode plot, how it is varied, and also we have seen the different controllers which are known as the PID controllers. We have seen the effect of PID controllers in improving the system response. Okay, so with the help of these controllers and with the knowledge of these controllers, so tomorrow we are going to discuss about the compensators. Okay, so here PID controllers will give you the one type of response, and the same responses can also be obtained to improve the system performance specifications. Now we are going to discuss about, tomorrow we are going to discuss about the compensators. Okay, so with this compensators, tomorrow I will close the fourth unit. Then in the next class, we will discuss about the classical design, which is known as the state space analysis. Is it clear? So I will send you this PPT also, all of you. Just you go through this PPT. Yes. Okay. Thank you all. Good afternoon.